This lesson deals with lab number 1, which is an introduction to the oscilloscope, function generator, and digital multimeter. In this lab, we're going to use an oscilloscope, or just scope for short. This is an instrument which will display voltage versus time. The scope we're going to use in this lab is also a 2-channel digital storage scope. The 2-channel means that we can observe 2 different voltages at the same time. And digital storage means that a voltage is converted to a binary number, it's stored, and then it's converted so it can display it on our PC monitor. Suppose we display on our oscilloscope 3 times the sine of 2 pi 1000t. Here's what the picture would look like on our oscilloscope. A perfect sine wave. We're seeing 2 cycles here. This triangle over here indicates the 0 volt reference. In other words, this is 0 volts and this is positive and this is negative. On the side over here are the scales. The y-axis scale is 1 volt per division. Now these are the major divisions here. So there's 1 division, 2 divisions, 3 divisions. So 3 volts. Also have an x-axis, which is time, marked down here. It's actually labeled starting here. We're going to move that around in some of the experiments. But here's the x-axis scale. It's 200 microseconds per divisions. Again, these are the major divisions that are here. So 1, 2, 3, 4, 5 divisions times 200 microseconds. That would be 1,000 microseconds. And that would be 1 period. And the reciprocal of that would be the frequency. So 1 over 1,000 microseconds is 1 kilohertz. So here we've got a 1 kilohertz sine wave with a peak value of 3 volts, which means it goes up to 3 and down to -3. This other triangle over here is where we're triggering the waveform, and we'll see things about that a little bit later in the course. And here are those calculations that we just talked about. 6 major divisions with 1 volt per division gives us a 6 volt peak-to-peak sine wave, or 3 volts peak. 5 divisions with 200 microseconds per division, so that's 1,000 microseconds, and that would be a period, and so the reciprocal of that would be frequency, and that would be 1 kilohertz. In ECE 201, we introduced a resistor. Resistors have their values marked on the body of the resistor in a variety of ways. One way is to use 4 bands of color, where they're oriented this way with a space on the right-hand side. And these colors tell us the nominal value of the resistance. Colors that can appear on these bands, the first 3, are black, brown, red, orange, yellow, green, blue, violet, gray, and white, and those correspond to 0 through 9. The 4th color is either gold or silver, or is actually left blank. And there's no paint. So each of these bands are placeholders, and let's see how we can put together the nominal value of resistance. The first band is a placeholder, the second band is a placeholder, and the third band is the power of 10. And then the 4th band tells us the tolerance of the resistance. Let's do an example. Suppose they have a red, violet, yellow, gold resistor. Red corresponds to 2 above, violet 7, and yellow 4. So it's 27 times 10 to the 4th, which would be 270 times 10 to the 3, which should be 270K. The fact that it was gold is a 5% tolerance. So this resistor is nominally 270K ohms, but it ranges 5% above and 5% below that number. So in other words, 1 minus 0.05 times 270K, and that's 256.5K, and then 5% above 270K is 283.5K. So our resistor lies somewhere between these 2 values. We're going to use some instruments in lab to measure resistance, and we'll be able to find their value within a tighter range than this. But it gives you an idea of the range of values that you might have for a 270K resistor. In our lab, we're going to use a Mastech digital multimeter, in particular model MS8217. We're going to measure several things with this meter, but one of which is going to be resistance. And the way the meter works is that it sets up a current source to create a voltage drop across an unknown resistance. And by measuring the voltage across that resistance, we can calculate the unknown. Here's a pictorial description of what's happening. Here's a current source. It's going to flow through a wire, through our sample, back through a wire, back to here. Now, if we have an ideal voltmeter, this doesn't draw any current, but in a real voltmeter, we're looking at a very, very small value of current. So basically, all of this current goes back through here. Let's take a look at maybe writing an equation for this on the next page. We have a current source, and across it is a very high resistance meter, which you can think of as an open circuit. We have a wire going from our terminal to our unknown resistor, and then another wire coming back. So doing Kirchhoff's voltage law, the rise in voltage would equal the drops around the loop, but we have a common current I. So that current times this resistance is this voltage, same current times this resistance, and then the same current times this resistance. So we have the following equation. The voltage V is equal to I times the resistance of our red wire, our unknown, and our black wire. Pull out the common I. we've got the sum of those three resistances. Now, if our unknown resistance is much, much bigger than the wiring resistance, then we could throw these terms away. We've been measuring our unknown sample. Well, what value of wiring resistance could we expect? For the banana grabber wires I'm going to use in lab, this is about 50 milliohms. Measuring things in the k-ohm range, so pretty much these are negligible. If you had thinner wires, you could be seeing resistances on the order of half an ohm. Let's next take a look at the accuracy of our multimeter. The Mastech MS8217 is referred to as a 3 3/4 digit multimeter. What that means is that you can have 4 digits displayed that can go from all zeros to 3 3/9. Now this digit can go from 0 to 9, so can this one, and so can this one, but this one, because of the A to D conversion, can only go between 0 and 3. So we got 3 as the highest possible value out of 4 digits that are here. So referred to as 3/4 of a digit. Kind of an odd way to describe that, but that's what that means. Let's take a look at an example to show you what the accuracy of a particular reading would be. It turns out the accuracy changes on different scales. I'll have to refer you to the manual to see what the errors are for each setting of the selector switch. I took an example with a 40 k-ohm range on my reading. In other words, I can go up to 39.99k. In the manual, it says that the accuracy is plus or minus 0.5% of the reading plus 2 digits. Let me show you what that means. So if I were to read a value of 13.34k, what's implied here is that there's a window around this number as to the actual value that I'm reading. Just like a tolerance in a resistor, we know it falls within a range. And this is true of all instruments, that when we measure something, it's not exactly the value we see displayed, but in a window of possible values. So how to interpret the accuracy then is to take this number. It says here to take 0.5% of that, so we're going to multiply that by 0.005, which is 0.5%, and just take the exact number that's here, and this is what I get as a result. Now it says you have to add 2 digits. This is from the digitizing of the signal. What that means is if you have 4 places here, wherever the decimal point is, record that, and then it's saying to put 2 digits. I have a lot of possible numbers here, but 2 digits refers to just this last place being a 2. But again, the unit was K, so you have to include that also. Now if it was 7 digits, you put a 7 here. If it was 10 digits, you put a 10 here. Depending on the scale you're on, this is going to change. So if you have a lot of leading zeros, this is going to dominate the error. You want to have as many digits out here as possible. And it does that in the auto ranging. Now you add these two numbers together, and this is your accuracy. So it's plus or minus 0.0867. What we're going to do is we're going to add and subtract that from this reading. Let's take a look at that on the next page. If we take our actual reading and then subtract and add our results on the previous page, we wind up getting this value and this value. And what that implies is that our actual value of resistance is somewhere between these two numbers, 13.2533K and 13.4267K. Even though we read 13.34K, the actual value is going to fall between these two. So when you look at this, what you're seeing is that these two digits are the same. So what this means is that we can rely on the first two places, and the last two begin to fall into our window of accuracy. Lastly, a few comments about the wires and connectors we're going to be using in lab. Our analog discovery, we're going to use an adapter board to get better connection to our circuit. And they're going to be using what are called B and C connectors. B and C are the initials of the engineers that invented this type of a connector. We typically have a male and a female connection where we interconnect these two and then rotate it. These little tabs lock together. And it creates what we call a continuous shield. The cabling itself really consists of the following. There's a wire in the center surrounded by a dielectric, typically Teflon, and then that's surrounded by a braided metal shield, and there's a plastic jacket over that. So what we really got is a conductor, and then that's surrounded by a conductor. That's going to be our ground. This is a very good type of a connector for very high frequency work. Now most of our stuff we're going to be doing is in audio, but many of our connectors will have B and C type connections. And if we look at later courses, we'll be worrying about whether our wires themselves will be interacting with our measurements. So even though this is not real critical for what we're doing in audio frequencies, it's something that we need to start to think about. The main type of wire we're going to be using is a banana to grabber wire. It consists of called a banana connection here, which looks like a banana that's been peeled and put back together again. This makes a nice spring contact to get a good connection. And then the grabber has a little sleeve on it, and a little hook's exposed when you pull on this piece of plastic that's here. You can grab onto an element in a circuit. We're using a solderless board, and wires kind of pop out of there very easily, so we're going to use test wires and then connect with these grabbers. This type of a connector is okay for audio frequencies, but would not work well at radio frequencies. Now, there's two other things we could possibly use in this banana to banana wire with an alligator clip. In other words, you can kind of make your own grabber. I'm not recommending this for the course, but it's another option. So we get a banana connector here like this one, and then this one, this alligator clip fits inside of it, just goes right on this end over here. You can kind of grab onto things too. Now in the parts list, I'm going to recommend buying a higher quality banana to grabber wire. You want to invest in pieces of equipment that you have so they'll last a long time as you begin to take more and more measurements and do more and more investigations. Now the rest of this is the lab itself. And with every lab, I like to put a purpose. In this particular case, we're looking at the oscilloscope, the function generator, and digital multimeter as our basic measurement tools. With every lab, I also have concepts that I'm covering. In this particular case, we take a look at the resistor color code and the accuracy of components and also our digital multimeter. Every lab will have some laboratory technique. In this particular one, we're going to learn how to use the Analog Discovery USB oscilloscope. It has an arbitrary waveform generator, which we'll call a function generator. We're also going to measure voltage, amplitude, and time using the oscilloscope. And we're going to measure resistors with our digital multimeter. This is the background material you need for lab number 1.